welcome everyone. Thanks for joining for this session. And actually, I will have to stay here because I have to move some of the slides that have a couple of builds in them. Thanks for joining this talk. I'll be talking about confidential computing and specifically its application on RISC-V platforms. I'll be focusing on application class processors. I think there was another talk earlier that that Dingji and others did on talking about IoT sort of applications as well. My name is Ravi Sahita. I work at Rivos right now. In the past, I've spent a bunch of time working at Intel on security stuff still. So this is a quick outline for the talk. I'll briefly introduce confidential computing. If folks are familiar with it, it'll be a quick refresher. If folks are not familiar with it, hopefully it'll help give some background. I'll talk a little bit about the threat model specifically for confidential compute, since it has certain nuances that are different from traditionally the way people think about platform security. Then I'll present a reference architecture that we've been discussing for confidential computing on application class processors in the TG that is appropriately called APTI, or Application Processor Trusted Execution Environments. And we'll break it down, I'll try to break it down into three aspects, right? From a practical perspective, what are the implications of building such an environment, and what are the implications on platforms and SOCs? What are the ISA implications? Some of those that we've started to discuss in the APTI TG. And it's sort of in reverse order, but where we focused on in the APTI TG right now is some of the non-ISA interfaces, the software ABIs, which from past experience and working on this kind of stuff for a while is really the place where you want to start, specifically for application class processors, to make sure that you're sort of aiming in the right direction to be able to bring on a lot of the workloads that people want to run in these environments without making too many compromises on performance and scalability and resource sharing, etc. And then I'll end with a call to action and a brief status on the APTI TG that has been working sort of formally for the last 3 months or so. We made some good progress because of a lot of good interest that we've had from the security community in RISC-V. A lot of new people joining the group that have contributed. We've gone through and done like a design survey of various architectures in this space. So I'll talk about. I'll point to some resources that we've built as part of that. So a quick intro on confidential compute. Really, what confidential compute aims to focus on is data in use protection, right? So traditionally, when you think about data confidentiality and integrity, there's been obviously a lot of work done in protecting data when it's in storage, right, and it's persistent storage. And when data is in transport, so you have network protocols and various varieties of those depending on your application that can protect data in transit. And the confidential computing architectures want to take the next step and sort of provide even more control over the TCB that has an influence on data that is in use within a compute complex, right? And so typically the way confidential computing is implemented is by virtue of using a trusted execution environment, right? So for the trusted execution environment, what you have to call out is what exactly is your trusted computing base. And the mechanisms by which you prove that trusted computing base is called attestation. And that process is typically rooted in some hardware-based mechanisms in order to prove to a remote relying party that you're running a trusted execution environment with an immutable hardware root of trust, right? And that's sort of the strong properties that you want to prove. And this is a general definition that sort of the broader confidential computing consortium, which is sort of an industry group of practitioners from various architectures, have been using. And it's a broad definition that is to be viewed as sort of independent of what mechanisms are being used to enforce these properties. So that's the part we are looking at in the APTI TG is boiling down sort of what does this mean in terms of the software mechanisms? What does this mean in terms of the ISA support that we need over and above what we have right now? And then what does it mean from a practical perspective when somebody is building a SoC and a larger system with these properties. It also makes sense to pause and look at some of the applications that would benefit directly from these sorts of, from a confidential computing architecture, right? And the general property that we see in application class processes that are building confidential computing is multi-tenancy, right? So in a lot of these environments, there are multiple actors that have different motivations and different trust properties that they want to achieve, and they're all operating on the same platform. So a very common example is sort of a hyperscaler multi-tenant cloud environment, right, where a cloud platform is hosted and the hosting entity has a number of actors and entities involved in putting that system together, right? There's the cloud operator, there's developers, there's third-party software that's running, there's management software, provisioning, orchestration stuff. And then there's the tenant, which is really trying to reduce the TCB and make sure that it has a strong binding to the platform and is really running with a lot of these other entities outside the TCB. You see a similar pattern in other environments like multi-domain platforms where you have isolation required for other requirements. Like we saw this nice talk yesterday or day before on the safety and security together, right? So that shows up in a lot of the multi-domain platforms. Then you have deployment models like edge-based deployments where a platform or a device is out of the control of the entity originally provisioning it, and so it's exposed to a lot more of the attack surface, like physical attacks and things like that. And then finally, you have environments where you have different geographies or different organizations sharing data and operating on different data pieces to sort of achieve a bigger goal, whether it's multi-party, machine learning or other data analytics. And those are also interesting avenues where confidential computing helps to provide a place to stand for data such that the data parties can exchange trust assertions and also therefore apply some trust assertions on the data that or models that they're generating. And we see that in federated learning models, for example. So the common sort of thread between all of these is these are use cases that want to maintain data confidentiality, they want to maintain data integrity, they want to maintain some notion of chain of custody and provenance for the data, right, as it's being processed. So I made the statement earlier of hey, we need a hardware-based TE to support confidential computing. And there are some properties that we want to derive out of such a hardware-based TE, right? So the primary properties we want are data confidentiality and integrity. This is ensuring data that is owned by a tenant or by a data owner does not get divulged in an unintended manner or in a malicious manner. The data processing preserves its integrity so that the entity that's operating on the data knows that if it writes to the data and then reads it back, it's going to get the same data back and not get modified by some unknown entity. Having some notion of integrity on the code that they're executing, right? What processing were they intending to do and did they actually process the data that way? And then finally, attestability of the fact that, how do you prove these properties, right? There are also some additional desirable characteristics like confidentiality of the code. You might have some IP or DRM-oriented scenarios. Authenticated launch, more from the perspective of the relying party, right? Knowing that the relying party can ensure that a specific workload was executed before the data is given to that workload. Programmability and recoverability. Recoverability sort of goes hand in hand with the attestation properties. Anytime you have a TCB reporting system, you also want a TCB recovery system that goes with it. Otherwise, you run into problems. And the programmability sort of goes with the flexibility and scalability aspects of it. This is a short sort of treatment of the adversary and threat model. Obviously, one could have multiple days of discussion just on the adversary and threat model, since it can be so diverse across these different use cases. But this is a sort of a quick treatment for when we think about adversaries. It's good to kind of think about what are the different classes of attacks and who can perform those attacks, right? So in a sort of compute system, we want to cover things like system software adversary or software adversaries in general. That includes system and user mode software. Hardware adversaries that you can sort of bucket at a coarse granularity into simple hardware attacks, which are much easier to implement for somebody who has physical access to the system, from advanced adversary attacks where somebody might break down the system or components of the system to really extract keys and things like that with much more invasive techniques. And that's what you sort of see on the right-hand side is like these three adversary capability, approaches or entities can launch any of these combination of attacks, right? Starting from very basic attacks on the software infrastructure that is, part of your TCB, to protocol attacks on the various, protocols that are being used to exchange data, set up or configure the, security mechanisms. Cryptographic attacks, like, hey, I'm encrypting memory, but if you're not using the right, encryption schemes or the right encryption key strengths, you basically are, it's sort of like, it's a moot point. And anytime you create sort of these barriers, whether it's access control models or encryption models, you have to worry about sort of side channel attacks, right? And these are micro-architectural side channel attacks, architectural side channel attacks based on, creating contention with shared resources are all important aspects to look at. And then finally, as we're talking about sort of the hardware ecosystem, and we saw a lot of discussion this time around on using chiplets and system of chiplets, we have to also consider issues about supply chain. Since we're trying to create a model where we can attest to the hardware and software TCB, the hardware TCB attestation is an important target for these sorts of supply chain attacks. Where, if there is any tamper of hardware or firmware elements that are part of your system integration, those are avenues of attack points. And then some of the hardware attacks similarly, as I mentioned. And we also have to recognize that this is sort of a very broad sort of treatment of the adversary and threat model. And as we look at creating these interfaces that we're proposing in the TG, different implementations, depending on the use cases they're targeting, will have varying degree of protection or resistance against these attacks, right? And that's something we kind of recognize as a group. But as we're writing some of the security recommendations, we're trying to be sort of as complete as possible, knowing that some mitigations somebody deploys maybe less, and somebody might go all the way. So let's start looking at the different pieces of the architecture, right, in the confidential computing reference architecture. So this is sort of just a reference picture for a privileged ISA that we have today, like for an application class processor, showing basically a multi-tenant model, right, a privileged software entity running an operating system and a VMM on top of a hardware with some M-mode firmware running a number of VMs. So the first question sort of we were asking ourselves is like, hey, we want to be able to use the hardware abstractions that allow us to bring in the most of the software workloads with the minimum amount of friction, right? So as we sort of create these TCB boundaries between privileged software and the TCB, we have to sort of think about what is the place to stand in the firmware, what is the place to stand for the TCB elements in privileged software, so that we can protect the actual workloads. The workloads are sort of running at the topmost level in these VM tenants, right? So what we did there was, and one point I wanted to make here, sort of we started with this model because we felt like the hardware virtualization or the hypervisor extension in RISC-V already gives us a very nice abstraction for some of these workloads in terms of isolation boundaries, right? And whether you want to deploy a VM in this multi-tenant environment or a container within that TVM or a set of processes, it gives us that sort of software flexibility to be able to use to do that once we have support for the different modes in the TVM or the TE virtual machine. So the way we kind of broke down this TCB is we first introduced this notion of a TE security monitor, right? And that's sort of an entity that we use to essentially enforce the security properties for the workloads that are being hosted on the platform. But the important point here we wanted to ensure is that we wanted to still retain the resource management capabilities with the platform owner, which is the host OS or the VMM, owning these various resources on the platform. So as part of that, the TSM essentially, that sort of solves two problems for us. One is it doesn't replicate all the complexity in the TSM because we don't have to bring in all the resource management parts in there. It lets us focus the TSM on enforcing the security invariants we want to for the properties we want to achieve. And it keeps it minimal from a security perspective and low complex, reduces the complexity. To support that kind of a model where you see like, hey, we need a first level isolation between these host operating systems and the TSM, we require some support from the platform, from the CPU or from the firmware. And that's essentially achieved through this TSM driver component that you see in M mode firmware. Now you might be thinking about like, hey, but we still have a TCB problem that, we have other M mode firmware potentially sitting next to this TSM driver, which is an important capability to enforce the TSM. So we're looking at sort of what is the right mechanisms there to essentially reduce the TCB there further. One potential approach I'm showing here is like deprivileging some of the other untrusted M mode components into the existing, lower privilege modes, right? Like S mode or U mode. And there are other sort of options being discussed in our trusted computing SIG as well, right? Which might give us other options for reducing that TCB. But in the APTI TG, we were sort of focusing on creating the right interfaces, right? So that this TEI interface that you see there is basically broken down into a host to TSM ABI and a guest to TSM ABI, and really focusing on what are the intrinsics that we need here that a TSM should support to give us all the right properties that we need for the workloads we want to support. And that's the non-ISA interfaces we'll talk more about today. There are a few simple ISA extensions that we are also talking about, like for example, in the architecture, introducing the notion of a confidential physical memory attribute, right? So what we care at the platform level, at the architecture level, is how do we express the notion of confidential memory? How that confidential memory is actually access controlled on the platform, whether it's encrypted through the memory controller or it has an additional MMU support, etc., are really up to the platform implementations that implement that interface. Right? The other part that we've been talking about is how do we secure the interrupt mechanisms, right? So today we have AIA, which gives us nice memory-based mechanisms to essentially bind guest interrupt files to virtual CPUs, right? If we have the notion of confidential memory, we can very easily extend those mechanisms to also secure the guest interrupt files. So that those are mechanisms that we've been discussing in the TG. And then last but not the least, which is an important aspect we want to capture, even though it doesn't cleanly fall into our ISA and non-ISA differentiation, right, are the platform properties that we want to capture. Like how do you support the notion of this TCB, right? Where do you start the measurement of this TCB from, right? So there are different elements in the platform, some canonical elements that we sort of expect. Again, we don't want to be prescriptive about how these are implemented, but there are certain properties we desire, right? And those are essentially broken out here into, how do you enforce the memory isolation properties, or how do you enforce the notion of confidential memory? What are the properties from the root of trust that we desire in terms of attestation? And then once we get to assigning devices to these confidential or TVMs, what are the properties we want from the SOC in terms of IMU extensions, right? And that's sort of a third example. And these all platform properties, we expect those to essentially feed into the RVI security model spec that we've been discussing. There's a separate TG for that, as well as a security architecture analysis we'll do of the APTI interfaces, which will sort of feed into this as recommendations. So now that I've introduced sort of the rationale for some of these architecture pieces, let me call out some of the sort of the salient points of this architecture, right? So I called out this particular point where this sort of partitioning of the TCB allows the OS VMM to retain its resource management role. So we'll see the sort of the implications of that in the ABI, right? And why that's a good property to have, because there's obviously a lot of complexity in the OS and VMMs with third-party kernel drivers and extensions for scheduling and memory management, etc. And we don't want to bring all that complexity into the TSM. We introduced this new min TCB component called the TSM, right? It reuses, the nice parts about that are this reuses the hypervisor extension mode of the privilege ISA, right? Which we expect to be implemented and applied widely for virtualization, for hardware virtualization. And it gives us a good security boundary that we can build on, right? And as described here through this THABI that I'll show you an overview of in a second, the OS VMM effectively yields the enforcement of these security properties to the TSM, right? So the OS VMM still retains control of managing these TVMs, scheduling them, etc., with the property that it doesn't have access to access any of the memory or state associated with those TVMs, right? The corollary to this kind of a model is that the one particular attack that's clearly out of scope for us with APTI is a host denial of service. So the host is always in control of these resources. The host can always stop a TVM from executing, right, or starve it in terms of resources. And that's an acceptable, attack in our model because we are trying to really protect the confidentiality of the data, right? And we're not as much worried about availability. In some deployment models, availability may be a required aspect, and that will have to be addressed by other platform mechanisms. And then last but not the least, as I said, we are sort of focused on the ABI because that lets us cleanly define the properties of this TSM driver and specify how it can abstract the platform properties that we require, right? So, for example, the roles that this TSM driver achieves in this model is that first, bootstrap isolation of the TSM, a secure context switch between the OS and the TSM, and then supporting some of the attestation mechanisms or interfaces to the platform through the root of trust. And you'll see those aspects sort of called out in the THABI. So a little bit about the root of trust properties, right? As I said, it's kind of pointless to do confidential computing if you don't have a strong hardware attested model supporting it. So what we're prescribing in the security recommendations is basically to build the root of trust chain in a independent way for confidential compute on the platform. And this could be in addition to other trust chains that are built on the platform for platform, secure boot and things like that. But it reuses a lot of those mechanisms in the root of trust to essentially build the root of trust through the hardware root of trust into the the TSM driver, and we can debate on like how do we really partition that TSM driver out into the TSM and then eventually into a TVM. And the nice property this gives us is we can now delegate that trust authority, right, to those TCB elements at the right layer. So when a TVM comes up, it can be provisioned with the right certificates so that it can support attestation, right? It can also extend its trust, in different software components that it loads through the TSM and have the TSM essentially be the trust authority for it, right? And it gives us a nice decoupled architecture which we can now update, in a modular manner as well. And so that's what this example is trying to show. I won't, obviously in today's talk, we don't have enough time to go through all the details of the different attestation protocols. I'll just give you sort of a short view of like, what is the model we want to use for attestation. But that's sort of the general idea is once you have this trust chain built up, you can support, very standard X509 extension-based attestation evidence schemes that can be supported with, again, very standard attestation protocols that IETF and other groups are building to support various attestation schemes. Right? Yeah, and the other point that I called out earlier is having this sort of construct for the container, for the TVM that we're building, allows us to supports both user and supervisor within the TVM, right? Obviously with the virtual bit enabled, and that gives us the right sort of software abstraction where somebody can bring into the TCB the kind of software support they need, right? So for example, somebody could run a traditional Linux VM guest with specific applications, or somebody could run a very specific runtime with specific applications supporting it, etc. Right? And we've seen some nice examples of this if you look at some of the projects happening in the confidential computing consortium, examples like ENARCs, right, where they're essentially using the same construct of a hardware virtualized TVM, but then pairing it with a WASM runtime and a WASM application. So you can really fine-tune, once you have the hardware modes available, you can really fine-tune what your trusted workload looks like. And then you back it up with the right attestation properties. The other nice part about using this abstraction is makes supporting future ISA that much more easier. As we add future ISA, we will do it with the mind of supporting the hardware virtualization modes as well for those ISAs. And so having this construct, for example, as we are talking about CFI mechanisms that we just are in the process of discussing right now. And we would like to use, obviously, the CFI mechanisms within the TSM. We would like to use it within host software. We would also like to use it within the TVM to harden the runtime of the TVM itself, right? And we can do it with that much more ease if we rely on this sort of partitioning scheme. So with that sort of intro, let's look at these 4 areas, which I sort of selected because these are sort of the big areas that have an implication on the sort of the community here in terms of building RISC-V-based platforms. What do we need from the hardware root of trust? What are the mechanisms we need fundamentally for state protection? And that includes both memory and register. What other platform protection schemes do we need to think about given all the other things that are happening on an application class processor in terms of debug, QoS, things like that. And then also looking to the future a little bit, a platform is no more just one type of processor. You have multiple types of processing elements on a platform. We need an architecture that sort of extends the ability for doing device function assignment. Just like we're doing it for commodity or ordinary VMs, we should be able to do it for trusted VMs as well in a performant manner. So what's the trust model for that look like? So in the first one, I described sort of the transitive trust chain that we want to build. And for the root of trust, we desire certain properties, right? The reason we want this to be hardware attested or hardware backed is because we want a very strong unforgeable property for the hardware root of trust. And we want a property that allows us to revoke certificates on the hardware root of trust and also be able to update firmware and do TCB recovery, etc. Right? Some mechanisms for hardware attestation root of trust also require anonymity, but that sort of depends on your application. Right? And so this sort of is like a very high overview on the attestation model that we can expect. It's sort of a canonical model used by most architectures that are implementing confidential compute, right? Where you start from a hardware root of trust at the bottommost layer that might have that necessarily has immutable components, but it also may have mutable components like ROM firmware extensions, etc. We want that obviously to be measured and recorded in the hardware root of trust, but that acts as the security authority for the next layer. So if people are familiar with some of the trusted computing group terminology, this is sort of specified in the TCG DICE architecture, right, as one manifestation, right, where you have a device identity composition that a lower trust layer performs and measures and then transfers control to a higher trust entity while it provisions secrets into it, right? And so that's sort of the chain you see here where the ROM and the M mode firmware, the TSM driver specifically in our case, would provision, after measurement of the hardware and software TCB, would provision secrets into that next layer. So in that case, this would be the TSM would be one good example, but it might also measure other firmware TCB elements on the platform depending on the SoC, composition. That hardware and software TCB together can now act as the secure authority for any TVMs, right? And we want the ability to obviously run multiple number of TVMs on the platform. We don't want a limit there in terms of the physical limits are really just the amount of memory and compute resources you have on the system. And that TVM can, once it's bootstrapped, it can request additional evidence from its trust authority, which is the TSM, right? So those interactions are captured in the THABI, or rather in the TGABI, because this is an interaction between the guest and the host. And the TVM can now be challenged by a remote relying party, right? So the remote relying party can essentially issue a challenge, which typically is a nonce in many of these protocols, and can say, hey, prove to me that you're running on a hardware rooted TCB, right? And so when the TVM responds with a nonce, evidence that is based on the certificates that's provisioned by the TSM, it can essentially prove that entire trust chain back to the relying party, right? And that essentially sort of allows the verifier or the relying party, and I'm sort of showing that as one entity here. In sort of standards protocols, you might see those as separate entities. You might see a separate verifier providing trust assertions to a relying party. But then it can now provision data into the TVM, after it has verified the trust chain and the expected measurements, right? So since the root of trust is managing the SOC lifecycle, right, it has like very stringent requirements on its security, right, and it has very strict debug authorization requirements and things like that. So one of the aspects we were discussing recently in the APTI ETG is how we use the root of trust to essentially bootstrap the debug authorization for the SOC, so that we can very cleanly recognize whether this platform that's supporting confidential compute is in debug authorized mode or is it in production mode, right? And if it's in debug authorized mode, then we require that trust chain to essentially be completely differentiated from the trust chain you would use when you're in production mode, right? So that a relying party is never fooled into thinking that it's talking to a TVM, while the TVM is being actively debugged or the platform is being actively debugged. The second aspect on the platform is this notion of creating a confidential memory model, right? And we feel like the best way to sort of articulate that is through the notion of a dynamic PMA. So RISC-V has the notion of physical memory attributes, which may be static or dynamic. Static ones are typically configured as part of the platform or the CPU setup or the platform setup, and dynamic PMAs are things that can be reconfigured by some system software, right? So that's sort of left open to interpretation. What we want to do here is specify clearly this notion of a confidential memory PMA that is managed by the TCB, right? So in our case, the TCB would be the hardware root of trust, the TSM driver, and the TSM, right? Once you have that construct, we have to sort of provide some mechanisms in the platform of how that dynamic PMA is assigned or revoked, right? So we describe mechanisms of converting memory from non-confidential memory into confidential and vice versa on the architecture. And on the left-hand side, you sort of see one example of an extension of an MMU that can essentially take a physical address, right, apply a memory tracking function to it, and the memory tracking function could be manifested in different ways depending on your implementation, but it essentially results in this confidential or non-confidential PMA being resolved, right? So having that construct allows us to essentially apply very clean access control rules on which entity on the platform, depending on the mode they're executing in, can access confidential memory or not, right? And now we can clearly start building a model where we can say, hey, once memory gets converted into confidential, the host automatically sort of yields access to that memory, right? And we can enforce that through this IMU extension for memory tracking. So that's sort of the model being showed on the left-hand side. On the right-hand side, what I'm showing is, yes, this MMU extension can take care of enforcing these properties on confidential memory, but implementations may still want to, that desire to protect against physical attacks, may still want to take that confidential memory indication and carry it on the memory fabric and internal fabrics to essentially encrypt the memory in a differentiated manner for that confidential memory region, right? And that is to essentially protect against rogue hardware attacks doing interposer and other sideband attacks on memory, right? So those are sort of some of the properties that we have to reason about. But from the ISA perspective, we need the ability to sort of specify, how do we convey the property of this dynamic PMA or confidential PMA, and then the platform implementations can take those indications and map those to the right security properties, right? And as I've noted here, some of these MMU mechanisms sort of work nicely also with PMP and IOPMP mechanisms if they're present on the platform, right? So in terms of the third pillar, so in terms of platform data protection, obviously there is a bunch of other explicit ways to access data while a workload is executing, right? And these might be through explicit debug mechanisms through the debug module, perfmon or performance monitoring mechanisms, right, that again are being actively discussed in the debug, trace, and performance monitoring work groups. And we have to be careful about these mechanisms, even though they're extremely desirable in terms of debugging the platform and profiling, doing runtime profiling, etc. We have to put some controls on these when we are running workloads that are subscribed to confidential modes of operation, right? So for example, for debug, we can basically take a stance as I was describing, hey, we have an authorization mechanism in the architecture. Let's use that mechanism and reflect those properties into our attestation that we do for these TVMs so that it's very clear to the relying party that, hey, this platform is under debug, or this TVM is under self-hosted debug. Where we have filtering mechanisms on the platforms, whether they're for performance monitoring, QoS, RAS, all of these mechanisms have some way of like tagging the data. So we can use that in addition to the extracting these TE signals on those fabrics and those buses to make sure that we can differentiate when those traffic elements are corresponding to workloads that are running as TEs or confidential workloads, so that we can apply appropriate policies on them. Reliability is an important one, specifically, starting with the root of trust, but also to the rest of the system, right? Anywhere we have these confidential workloads running, we have to sort of worry about, hey, what if somebody, changes, introduces arbitrary delays in the clock, does any voltage glitching or other attacks on the, so that has to sort of be a general design consideration with special focus on the root of trust, because that's sort of the most secure TCB element, but also applies to the rest of the subsystem. And then last but not the least, we have, as you saw sort of in our TCB picture, we would like to minimize the TCB when we're talking about confidential compute. But there is like privileged firmware running on the platform that does a bunch of configuration and setup for address decoding, other memory configuration, etc. So there is we want to sort of create a stage for where we can enforce explicit configuration integrity, so that we know that here's the configuration that firmware or the platform operator chose, but is now locked, so that when we go past that point, we know that we can trust that configuration. And that's sort of another aspect that we need to sort of call out explicitly. And then looking to the future, most folks here are probably familiar with the IMU extension that we've been discussing as part of the SoC infrastructure. One of the things we want to make sure we can do is, in a trustworthy manner, also assign devices to these application workloads, right, or TVMs, right. And so for that, we have doing something like that sort of introduces an additional class of attacks, right? Because now you're sort of bringing in some additional compute subsystem, because these accelerators are, basically, independent compute subsystems with their own firmware, their own compute, etc. And how do we bring that into the trust boundary, right? And the kinds of attacks we have to worry about are shown here. You could have ID spoofing attacks from these devices. The firmware on those devices could be modified. You could have reconfiguration attacks on the MMU corresponding to the DMA maps for these devices, etc. Right? So this is something we have to tackle systematically, right? In terms of making sure we can attest these devices. The good news here is, even though there's a lot of things to be done here, there's a lot of activities already going on in the other device, sort of interest groups or standard groups on this. So, for example, for device attestation, DMTF has already worked on a security protocol and data model, which can be used to interrogate a device to get its certificates and measurements, so that you can attest, you can perform whitelisting of certain devices, right? There is already a protocol in PCIe in place for enforcing the integrity and data encryption of the PCIe link. So once you attest the device, you can essentially securely program it over the SPDM session and ensure that the link is protected against spoofing or snooping attacks. Right? Once you've done that, the last part that we need to worry about is the host side. Right? On the fabric, as I was mentioning, as we carry these TE indications, how do we carry that over to the IMMU as well, right? So that it can recognize that when it's talking, when an authenticated device is talking to the system, to the host, or when the host is addressing an authenticated device for MMIO, those transactions are not being tampered with on the way, right? And so what I'm showing here is sort of a broad idea is the notion of the IMMU essentially having a secure personality or a secure interface, right? That we can essentially access control through a trusted register programming interface to things like that are in the TCB, right? So like we're showing here the TCB elements on the right-hand side, you have the TSM or the TSM driver overseeing the memory map that has been created by the VMM to make sure that once memory is assigned to a TVM that is subject to DMA, those memory maps are not tamperable while the TVM is using that device, right? And then in order to support the state machine on the device itself, the PCIe has been working on creating a protocol called TE Device Interface Security Protocol, or what is called here as TDISP, and that is used to enforce the state machine on the device. So if you have a device assigned to a TVM or a device virtual function assigned to the TVM can basically say whether it wants to use that device interface and at what point, right? So that you don't have time of check, time of use attacks on the device being used by the TVM. So this is a simple concept that allows us to essentially leverage the IMMU as we are defining it, right, in terms of preserving the page walk structures and things like that of the IMMU, and just providing it with the right indications so that when trusted transactions are coming in corresponding to a device, those can essentially address confidential memory without any additional performance overheads. And then last but not the least, I wanted to sort of give you a quick overview of the THABI now that we've kind of gone through like the platform concepts and what the TCB elements are and the non-TCB elements are. Let's look at a sort of a quick snapshot of what does the ABI look like, right? And what primitives are mentioned or described in the ABI to allow a host OS or VMM to manage a trusted context or a TVM, right? So we sort of split this into 4 stages, right? And it kind of helps think about, like I said, we want these intrinsics to be, small enough and simple enough that we can make the TSM itself very, very simple, right? And enforce some very, very simple invariants that we want to enforce. So we split that into these 4 phases. The first one is a pre-built phase. So you'll see ABI intrinsics that allow the host to essentially enumerate if a TSM is loaded and what kind of capabilities is it running with, right? And then the first sort of primary intrinsic is to allow the host to convert memory, right? So there is this notion of saying, here's a large swath of memory. I want to basically convert this memory using this dynamic PMA to confidential memory. And then that confidential memory can then be assigned at a later point as TVMs are actually being brought online, right? So we sort of separate the notion of converting memory at the global sort of platform level from actually divvying out that confidential memory between TVMs. Then when you build a TVM, the host, and a lot of these flows, by the way, are very similar flows to what a Linux KVM sort of model would go through, except they obviously have no restrictions on how they do that today because they cannot just access any of the host memory directly, right? Because of these intrinsics, we sort of put some checkpoints on those flows. So when you're building a TVM, you would allocate memory from the host memory space. In this case, you would do that essentially through the TSM, right? And saying, hey, I'm selecting confidential memory that I've already converted that I want to assign to a certain TVM, right? So that confidential memory then gets essentially used for a set of different assets corresponding to the TVM. So whether it's global controls for the TVM, setting up page table pages for the TVM, the data and code actual contents that get measured as part of the TVM launch, and then other control pages for virtual CPUs. So that's sort of the memory assignment. And as part of the memory assignment, we go through a process of creating the initial measurement construct for that TVM, right? That's sort of the static memory measurement aspect. And then the TVM essentially gets finalized to run. That finalization checkpoint is important because we want to make sure that there's a clean break between where the static measurements of the TVM stop and where the TVM can actually start executing, because we don't want that static measurement to change when the TVM starts executing. So the next phase is the TVM execution phase, where you essentially, the host again is being the resource manager, can start bringing vCPUs online or virtual CPUs for the TVM online, right? So this is basically entering these secure contexts, right? And that happens through the THABI. The flow essentially is when the host invokes a vCPU enter for a TVM, you essentially go through the THABI, which takes you through the TSM router, right? The TSM driver into the TSM, which then can basically activate a vCPU construct, right? So it lets us also firewall the functionality between the TSM driver and the TSM. When the guest is executing, in order to support the memory management model on the host, we have to support things like on-demand memory allocation, right? A TVM starts running and then it starts touching memory that is paged in. We have to do that with certain security invariants that are enforced, right? That this is applied only to memory that has not already been allocated as measured memory. So these are explicitly zeroed out through the TSM and these are new mappings that are created. We have to ensure that any interrupt delivery mechanisms that are being used to direct interrupts into the TVM are through these like secured guest interrupt files, right, assigned to those vCPUs. And then the guest may extend its measurements. So there are certain guest TSM ABIs defined so that the guest can come in and basically say, hey, I want to extend my measurement beyond what was statically measured, right? And this may be, and that will be verified by the relying party. And then finally, there are a set of ABIs defined to essentially let the host quiesce a TVM execution, which the TSM verifies before a TVM is allowed to basically destruct, right? And then once that is done, the memory essentially can be reclaimed or reassigned to another TVM. So that's sort of the life cycle. And if you look through our APTI ABI proposal, you'll see these 4 sequences measured, specified in there. A quick snapshot on where we are at in the TG, right? On the interface specs, the top 2, as you see, are like at the normative specs. They're all in one one interface proposal right now. They're split out by essentially a TH and a TG ABI. And that initial proposal is now drafted. It's an ASCII doc format, and there's a PDF version for people to review easily as well. So I would invite folks to help us review that and put PRs and issues, etc. on the GitHub. There is also an initial TSM implementation that is open source. It's implemented in Rust for 64-bit RISC-V, and that's available for people to start playing with as well. It implements the I would say about 95% of the TH and TG ABIs in there. And then there is some ongoing discussions with the hypervisor SIG and the Priv software, HCs and TGs to figure out how we collaborate on the host side aspects, right? Because we are touching some of the Linux KVM flows in order to be able to interface with other hypervisors, right? Like Linux KVM, and that's something that's something that we want to go further on. And we have some example guests in our TSM code base, but eventually we would want to run like proper Linux guests as TVMs. On the other parts of the charter, the requirements around what we want for the sort of the dynamic PMA and how we want to, what properties we want to enforce on it are documented right now. That is some discussion that will go forward, and we'll bring that into the sort of with a more more formal write-up into the privilege ISA TG. We've had some discussions with the IMU as part of the SOC infra SIG, and we are sort of writing down sort of what the requirements are, as I was showing on the other file, on the other slide. And then a lot of the other elements that are called out from line 3 onwards are platform specific, like implementations that have TLBs or caches, implementations that have QoS mechanisms or RAS mechanisms. And those are really going to be documented essentially as security recommendations or best practices, and those would essentially feed into our security analysis document, right? As a practitioner, these are the kinds of things you want to probably think about as you're building out this architecture. So I would like to basically sort of summarize it with this call to action, right? From my perspective, and we are seeing confidential computing also sort of being applied in other architecture platforms. I think it's a sort of a important security capability for us for RISC-V platforms to be able to provide that as a first-class capability for various workloads that may want to deploy these different use cases we were discussing. Please look through the specification. Most welcome to, we would love to have people join the POC efforts that we have ongoing, both on the TSM side as well as on the host side. And then as we add more compatibility tests into Linux KVM for RISC-V, I think those should also be extended for these confidential workloads, right? And we'd hope to do that as a follow-on step. I also wanted to thank a lot of the contributors in the task group so far, and hopefully more folks will join. But I just wanted to shout out to various folks that have been working with us in the TG, going through the design survey for different approaches, and working through the ABI mechanisms. So, yeah, there's some additional references for things that I referred to in the talk. Okay, I'll pause for questions, comments. Yep.
So I guess I'm a little confused as to why you think a single binary view of non-confidential confidential memory is enough for the use cases you showed. A simple way of asking the question is, I want to have two mutually distrustful TEs.
Yeah, so the idea is here, the binary sort of separation between confidential and non-confidential gives us the bootstrapping, because then the TCB elements, which is the TSM, can then essentially assign and isolate between the multiple, one or more TVM elements. So if you look at this picture that I was showing earlier, and I should have called that out more clearly. Yeah, this picture here. So yeah, I'll use this mouse. So as you see here, this sort of the main line here is isolating between the confidential and non-confidential memory type, right? Whereas this middle line here that you see is isolating memory that is confidential and is being assigned to different TVMs. So you can have many TVMs here, but that isolation is completely under the control of purview of the TSM.
I want to have two of those, because I can boot from mem mode and create two partitions that don't trust each other, have their own TSMs in each one.
Yeah, that's...
I mean, effectively, that's what you have here, except you have only two. You have the untrusted and the trusted. And this one, maybe you don't bother signing in the testing because you don't want to trust it. And that one, the only difference is you did that. But I could just have 3 or 4 or 5 of those. And
yeah,
if you go back to some of the use cases, that's what they want. And they're a bit worried about having all of that TSM, all the data in the same pool with no protection between them.
Yeah, so I guess, yeah, that's true. What you're describing can potentially be done. You could sort of create more than one context for the TSM to execute in, right?
Well, it's more than one TSM. TSM A, TSM B, because I'm Disney and I'm your health provider, and they don't want to trust one TSM. Yeah,
that's possible, but what we were sort of describing here is like if this TSM is small, transparent, and auditable, right, then it effectively becomes a macro code module that's part of the platform TCB, right? So then Disney is going to still have its own TVM that it'll finally attest to, but in the trust chain, it's like Disney is not deploying, in this model at least the way I'm showing is Disney is not deploying the TSM, right? They're essentially deploying a TVM. And before they're deploying the TVM or giving secrets to the TVM, they're verifying that they're satisfied with that TSM that's part of the TCB.
I guess my concern is, so I don't actually see how the confidential memory scheme that I'm paying PMAs actually provides much over the existing PMPs. It's just another label that can be handled in the same way. And if you're going to add more mechanism, you could allow there to be more than one TSM. It just seems like a very, not very forward-looking, right, to have this binary separation, and that's all. And I don't think I think it's, so now.
Yeah, so to your other point about
domains may want, and also people may want to use the hypervisor securely, their own one.
Right.
Not have to only have a guest OS functionality with no hypervisor functionality.
Yeah, so I didn't go into that. We can definitely go into that use case, but we do have a model where if you wanted to run a guest VMM in one of the TVMs, you could support that, right? You would need.
You could do it through recursive. You could do it through software traps and emulation of virtualization. Right? It's designed to allow that, but it doesn't.
Yeah. Ideally, you would use sort of a Paravert model to accelerate that, and that's sort of where Anup was talking about like some of the NACL interfaces. We could leverage some of those similar kind of interfaces here to run a guest VMM inside a TVM if desired. I mean, that sort of like was an advanced use case, so I left it out of the discussion here. But to your other point about the MTT, the reason we were describing the MTT as the construct as we showed was because we want to support the memory management models of the OS or the VMM, right? Which are not giving memory out in large physical regions,
no,
right?
So to understand, we need an improvement over just the simple register-based PMPs, right? But this is much less flexible than that is in many ways, right? Because you only have two compartments rather than multiple contexts.
Right, but it comes down to you still have many TVM compartments, right? The question is like, do we want one TSM as part of the TCB or multiple TSMs, right? Because the TSM function that's shown here is doing very simple things like.
If you have the multiple TSMs, the TCB of a guest TE is only the TSM driver. The TSM it is worrying about and its own code. It doesn't have to worry about the other TSM. That's the whole point, right?
Right, okay. Yeah, and that's really a matter of like, when you look at the TCB of the TSM, is that something people want to bring their own, or would they use one that is provided by
I think it's partly whether they trust it. It's also maybe the wrong API for them. They want a different program model. They want to run different OS, different hypervisor. They don't want to use the standard one because it doesn't match the use case.
I see. Yeah, I mean, that was exactly the reason why we sort of started at the ABI level to sort of understand like, okay, what are the intrinsics that a OS or VMM would need?
I guess the thing about, I've got Disney, I've got health provider, I've got people running air models, all these folks. And that security model is going to grow and grow and grow. There's a union of everybody's desires for what's in there, in that ABI, right?
Yeah.
And that's the problem.
I see, okay. Yeah, I mean, if I contrast it with some of the other architectures, right, they either provide ISA mechanisms that are implemented by the host OS, and the ISA mechanisms are the same whether it's a Disney or Bank of America or whatever, right? Or they provide intrinsics into other microcontrollers, which are again the same, whether, same and common part of the TCB.
I think we can do better than the existing architectures do. I think and I don't think it's hard. I think I think they came in with a very limited view of what needed to be done, and that ended up with a very limited design that doesn't support the future use cases. So I think we can do better than the existing ones.
Right, so yeah, okay, so you're suggesting like considering multiple TSMs in this model, and
it's more like, as with page tables, and every heart has a view out to memory. You're just talking about memory isolation with confidence. You're not talking about memory integrity or anything. It's just really isolation.
Yeah.
Can I touch this piece of memory? So every heart at any point in time, at any mode, has a certain view of permissions, what it can do. And across all the hearts in the system, you could have 300 different spaces if you wanted to, by having different tables representing the mappings, right?
yeah,
But if those tables, I guess the thing is the metadata in those tables is, does the current context have permission X on location Y?
right,
That's what the tables have in them, as opposed to, is location X confidential and is this process secure? That's like a much more limited model than the current context has this permission map. Right. So, and the problem is the cost of providing that permission map is about the same as providing confidential and unconfidential every page of memory. It's like, so to me, it's like there's no reason to have the very restricted and, I think inadequate model.
Okay.
Right. For the same hardware, you could have a more flexible model.
okay, right. James?
Yeah, hi, James Ball from Qualcomm. I got a couple questions for you.
Yeah.
On this slide here, what is providing the isolation between the host VM? Sorry, I'm distracted. Can you talk further away? Thanks. The host VMM and the TSM that are both in the HS layer. Is it the M mode? You've got the TSM driver. Is that going to be using like the PMP basically to provide isolation between the two things in the HS layer?
No, yeah, that's what I was trying to convey. Like the TSM driver bootstraps through this MTT like structure, right? Like a memory tracking structure, let's say, that enforces at a page granularity, the ability to specify confidential and non-confidential memory. So you can think of, as the TCB is being established, the TSM driver, which is obviously bootstrapped from the platform root of trust, can provide that initial MTT configuration to provide that first level of isolation, right? And from that point on, the TSM, which is running in confidential memory, can manage the properties of the memory beyond that initial bootstrap memory, right? So it is the confidential memory enforcement scheme that is bootstrapped as part of the platform initialization that provides that initial separation.
Okay, I'm not sure that's what I'm asking about though, but what prevents like what prevents, say, the VMM over there in the HS layer from trying to access some memory region that's in the TSM? I'm assuming it's a PMP.
Yeah,
Is
no,
that
so yeah, that's what I was describing here. It's in this particular case, because we are targeting an application class processor, we are relying on an extension of the MMU, right? So if you look at the figure there, right, whether you're walking in the context of a TVM, where you would go through a first stage and a G stage translation, or you're running in the context of the host, where you would only be going through the first stage translation, you would always enforce the memory tracking enforcement to say, hey, is this access confidential or not? And if you look at the sort of the logic, equation at the bottom, if that access on that heart is not coming in the context of a TE, those accesses to confidential memory would just basically be dropped by the MMU or faulted by the MMU. So once memory is converted to confidential, the host cannot directly perform load stores to that memory, right? And so that confidential memory is bootstrapped for the TSM by the TSM driver.
Okay.
Right.
Second question, can you go back to the previous slide? It was useful. Thanks. Yeah, so how does the system know which one of these different workloads or which one of these different VMs is actively making references out onto the bus or out to memory and devices like that?
So the idea is when the host VMM is still the resource manager and the arbitrator, right? So the scheduler is in the host OS or VMM. When it activates a particular TVM, it does that by saying, hey, I want to run this vCPU corresponding to this TVM on this physical CPU resource, right? The act of doing that is via an ABI intrinsic that the TSM exposes, right? So when it does that and the TVM actually is instantiated, that heart essentially is in TE mode of execution. And that is carried through in terms of address translation, cache accesses, etc. Right? So that's how the condition is carried forward through the fabric.
But so there's an ID that goes out onto them with the master board
So
of the processor.
what I'm describing here is at a minimal. You can think of it as a 1-bit ID, right? That says is this a TE context access or not, right? We could generalize that to like a multi-bit ID as well, right? But here you can think of it as a 1-bit ID with the isolation between the TVMs being enforced through the TSM through the G stage page tables that the TSM enforces.
Is there isolation between the non-trusted execution environments on the left here?
That's
three?
completely up to the host OS or VMM, right? We don't, like the TSM does not make any security statements about isolation between the non-confidential elements, right? That's completely owned by the host OS VMM through its paging structures and second G stage paging structures.
So you could have a situation potentially where maybe if you were talking, Christy was talking about having like, Disney and your health provider or whatever, if there's like, 10 different clients like that all running here, maybe they're all running in TVMs. So they can all have confidential computing. Nobody wants to nobody wants to be one of these guys in the upper left-hand corner
right,
here.
that's what I was trying to convey. Like the point, what this architecture is showing is that those TVMs would have to accept a particular platform's root of trust measurement, TSM driver measurement, and TSM measurement as the TCB, right?
Okay.
And yes, if there are scenarios where that last piece also wants to be unified, then we would have to support a model where a workload can say, I don't trust this TSM X, I want TSM Y, right? And that's something we will have to explore.
Okay, thanks.
Yeah. Other questions, comments? Okay. All right. Yeah, I'll be here. So actually, we have a security HC discussion right after, so we can hang out here.